The following is a conversation with Gary Marcus. He's a professor emeritus at NYU, founder of Robust AI and Geometric Intelligence. The latter is a machine learning company that was acquired by Uber in 2016. He's the author of several books on natural and artificial intelligence, including his new book, Rebooting AI, Building Machines We Can Trust. Gary has been a critical voice highlighting the limits of deep learning and AI in general and discussing the challenges before our AI community that must be solved in order to achieve artificial general intelligence. As I'm having these conversations, I try to find paths toward insight, towards new ideas. I try to have no ego in the process. It gets in the way. I'll often continuously try on several hats, several roles. One, for example, is the role of a 3-year-old who understands very little about anything and asks big what and why questions. The other might be a role of a devil's advocate who presents counter ideas with the goal of arriving at greater understanding through debate. Hopefully, both are useful, interesting, and even entertaining at times. I ask for your patience as I learn to have better conversations. This is the Artificial Intelligence Podcast. If you enjoy it, subscribe on YouTube, give it 5 stars on iTunes, support it on Patreon, or simply connect with me on Twitter at Lex Friedman, spelled Fridman. And now, here's my conversation with Gary Marcus. Do you think human civilization will one day have to face an AI-driven technological singularity that will, in a societal way, modify our place in the food chain of intelligent living beings on this planet?
I think our place in the food chain is already changed. So there are lots of things people used to do by hand that they do with machine. If you think of a singularity as like one single moment, which is, I guess, what it suggests, I don't know if it'll be like that. But I think that there's a lot of gradual change and AI is getting better and better. I mean, I'm here to tell you why I think it's not nearly as good as people think. But, the overall trend is clear. Maybe Ray Kurzweil thinks it's an exponential and I think it's linear. In some cases, it's close to zero right now, but it's all going to happen. I mean, we are going to get to human level intelligence or whatever you want, what you will, artificial general intelligence at some point. And that's certainly going to change our place in the food chain because a lot of the tedious things that we do now, we're going to have machines do. And a lot of the dangerous things that we do now, we're going to have machines do. And I think our whole lives are going to change from people finding their meaning through their work, through people finding their meaning through creative expression.
So the singularity will be a very gradual, in fact, removing the meaning of the word singularity, it'll be a very gradual transformation in your view.
I think that it'll be somewhere in between. And I guess it depends what you mean by gradual and sudden. I don't think it's going to be one day. I think it's important to realize that intelligence is a multidimensional variable. So, people sort of write this stuff as if like IQ was one number and, the day that you hit 262 or whatever, you displace the human beings. And really, there's lots of facets to intelligence. So there's verbal intelligence and there's motor intelligence and there's mathematical intelligence and so forth. Machines in their mathematical intelligence far exceed most people already. In their ability to play games, they far exceed most people already. In their ability to understand language, they lag behind my 5-year-old, far behind my 5-year-old. So there are some facets of intelligence the machines have grasped and some that they haven't. And, we have a lot of work left to do to get them to, say, understand natural language or to understand how to flexibly approach some, kind of novel MacGyver problem-solving kind of situation. And I don't know that all of these things will come at once. I think there are certain vital prerequisites that we're missing now. So, for example, machines don't really have common sense now. So they don't understand that bottles contain water and that people drink water to quench their thirst and that they don't want to dehydrate. They don't know these basic facts about human beings. And I think that that's a rate limiting step for many things. It's a rate limiting step for reading, for example, because stories depend on things like, oh my God, that person's running out of water. That's why they did this thing. Or, if they had water, they could put out the fire or whatever. So, you watch a movie and your knowledge about how things work matter. And so a computer can't understand that movie if it doesn't have that background knowledge. Same thing if you read a book. And so there are lots of places where if we had a good machine interpretable set of common sense, many things would accelerate relatively quickly. But I don't think even that is like a single point. There's many different aspects of knowledge. And we might, for example, find that we make a lot of progress on physical reasoning, getting machines to understand, for example, how keys fit into locks or, that kind of stuff, or how this gadget here works and so forth and so on. Machines might do that long before they do really good psychological reasoning, because it's easier to get kind of labeled data or to do direct experimentation on a microphone stand than it is to do direct experimentation on human beings to understand the levers that guide them.
That's a really interesting point, actually. Whether it's easier to gain common sense knowledge or psychological knowledge.
I would say that common sense knowledge includes both physical knowledge and psychological knowledge. And the argument I was
making... You said physical versus psychological.
Yeah, physical versus psychological. And the argument I was making is physical knowledge might be more accessible because you could have a robot, for example, lift a bottle, try putting a bottle cap on it, see that it falls off if it does this, and see that it could turn it upside down. And so the robot could do some experimentation. We do some of our psychological reasoning by looking at our own minds. So I can sort of guess how you might react to something based on how I think I would react to it. And robots don't have that intuition, and they also can't do experiments on people in the same way, or we'll probably shut them down. So, if we wanted to have robots figure out how I respond to pain by pinching me in different ways, like that's probably, it's not going to make it past the human subjects board, and, companies are going to get sued or whatever. So like there's certain kinds of practical experience that are limited or off limits to robots. And
that's a really interesting point. What is more difficult to gain a grounding in? Because to play devil's advocate, I would say that human behavior is easier expressed in data, in digital form. And so when you look at Facebook algorithms, they get to observe human behavior. So you get to study and manipulate even a human behavior in a way that you perhaps cannot study or manipulate the physical world. So it's true why you said pain is like physical pain, but that's again the physical world. Emotional pain might be much easier to experiment with, perhaps unethical, but nevertheless, some would argue it's already going on.
I think that you're right, for example, that Facebook does a lot of experimentation in psychological reasoning. In fact, Zuckerberg talked about AI at a talk that he gave at NIPS. I wasn't there, but the conference has been renamed NeurIPS, but it used to be called NIPS when he gave the talk. And he talked about Facebook basically having a gigantic theory of mind. So I think it is certainly possible. I mean, Facebook does some of that. I think they have a really good idea of how to addict people to things. They understand what draws people back to things. And I think they exploit it in ways that I'm not very comfortable with. But even so, I think that there are only some slices of human experience that they can access through the kind of interface they have. And of course, they're doing all kinds of VR stuff, and maybe that'll change and they'll expand their data. And I'm sure that that's part of their goal. So it is an interesting question.
I think love, fear, insecurity, all of the things that I would say some of the deepest things about human nature and the human mind could be explored through digital form. You're actually the first person just now that brought up, I wonder what is more difficult, because I think folks who are the slow, and we'll talk a lot about deep learning, but the people who are thinking beyond deep learning are thinking about the physical world. You're starting to think about robotics, in the home robotics. How do we make robots manipulate objects, which requires an understanding of the physical world and it requires common sense reasoning. And that has felt to be like the next step for common sense reasoning. But you've now brought up the idea that there's also the emotional part. And it's interesting whether that's hard or easy.
I think some parts of it are and some aren't. So my company that I recently founded with Rod Brooks, from MIT for many years and Roomba and so forth, we're interested in both. We're interested in physical reasoning and psychological reasoning, among many other things. And, there are pieces of each of these that are accessible. So if you want a robot to figure out whether it can fit under a table, that's a relatively accessible piece of physical reasoning. If you know the height of the table and you know the height of the robot, it's not that hard. If you wanted to do physical reasoning about Jenga, it gets a little bit more complicated. You have to have, higher resolution data in order to do it. With psychological reasoning, it's not that hard to know, for example, that people have goals and they like to act on those goals, but it's really hard to know exactly what those goals are.
But ideas of frustration, I mean, you could argue it's extremely difficult to understand the sources of human frustration as they're playing Jenga with you, or not. You could argue that it's very accessible.
There's some things that are going to be obvious and some not. So, like, I don't think anybody really can do this well yet, but I think it's not inconceivable to imagine machines in the not so distant future being able to understand that if people lose in a game that they don't like that. Right. That's not such a hard thing to program, and it's pretty consistent across people. Most people don't enjoy losing, and so, that makes it, relatively easy to code. On the other hand, if you wanted to capture everything about frustration, well, people can get frustrated for a lot of different reasons. They might get sexually frustrated. They might get frustrated they can get their promotion at work. All kinds of different things. And the more you expand the scope, the harder it is for anything like the existing techniques to really do that.
So I'm talking to Gary Kasparov next week, and he seemed pretty frustrated with his game against Deep Blue. So
yeah, well, I'm frustrated with my game against him last year because I played him. I had two excuses. I'll give you my excuses up front, okay, but it won't mitigate the outcome. Yeah. I was jet lagged, and I hadn't played in 25 or 30 years. But the outcome is he completely destroyed me, and it wasn't even close.
Have you ever been beaten in any board game by a machine?
I have. I actually played the predecessor to Deep Blue, Deep Thought, I believe it was called, and that too crushed me.
And that was, and after that, you realize it's over for us.
Well, there's no point in my playing Deep Blue. I mean, it's a waste of Deep Blue's, computation. I played Kasparov because we both gave lectures at this same event, and he was playing 30 people. I forgot to mention that. Not only did he crush me, but he crushed 29 other people at the same time.
I mean, but the actual philosophical and emotional experience of being beaten by a machine, I imagine, is to you who thinks about these things, maybe a profound experience. Or no, it was a simple mathematical experience.
Yeah, I think a game like chess, particularly where it's you have perfect information, it's 2-player closed end, and there's more computation for the computer. It's no surprise the machine wins. I mean, I'm not sad when a computer calculates a cube root faster than me. Like, I know I can't win that game. I'm not going to try.
Well, with a system like AlphaGo or AlphaZero, do you see a little bit more magic in a system like that, even though it's simply playing a board game, but because there's a strong learning component?
Funny you should mention that in the context of this conversation, because Kasparov and I are working on an article that's going to be called AI is Not Magic. And, neither one of us thinks that it's magic. And part of the point of this article is that AI is actually a grab bag of different techniques. And some of them they each have their own unique strengths and weaknesses. So, you read media accounts and it's like, ooh, AI, it must, it's magical or can solve any problem. Well, no, some problems are really accessible, like chess and Go. And other problems like reading are completely outside the current technology. And it's not like you can take the technology that drives AlphaGo and apply it to reading and get anywhere. DeepMind has tried that a bit. They have all kinds of resources. They built AlphaGo, and they have, I wrote a piece recently that they lost, and you can argue about the word lost, but they spent $530 million more than they made last year. So they're making huge investments. They have a large budget, and they have applied the same kinds of techniques to reading or to language, and it's just much less productive there because it's a fundamentally different kind of problem. Chess and Go and so forth are closed-end problems. The rules haven't changed in 2,500 years. There's only so many moves you can make. You can talk about the exponential as you look at the combinations of moves, but fundamentally, the Go board has 361 squares. That's it. That's the only, those intersections are the only places that you can place your stone. Whereas when you're reading, the next sentence could be anything. It's completely up to the writer what they're going to do next.
That's fascinating that you think this way. You're clearly a brilliant mind who points out the emperor has no clothes, but so I'll play the role of a person who says,
"You put clothes on the emperor? Good luck with it."
It romanticizes the notion of the emperor, and period, suggesting that clothes don't even matter. Okay, so That's really interesting that you're talking about language. So there's the physical world of being able to move about the world, making an omelet and coffee and so on. There's language where you first understand what's being written, and then maybe even more complicated than that, having a natural dialogue. And then there's the game of Go and chess. I would argue that language is much closer to Go than it is to the physical world. Like, it is still very constrained. When you say the possibility of the number of sentences that could come, it is huge, but it nevertheless is much more constrained. It feels, maybe I'm wrong, than the possibilities that the physical world brings us.
There's something to what you say in some ways in which I disagree. So one interesting thing about language is that it abstracts away. This bottle, I don't know if it will be in the field of view, is on this table. And I use the word on here, and I can use the word on here, maybe not here. But there's all that one word encompasses, in analog space, a sort of infinite number of possibilities. So there is a way in which language filters down the variation of the world. And there's other ways. So, we have a grammar, and more or less you have to follow the rules of that grammar. You can break them a little bit, but by and large, we follow the rules of grammar. And so that's a constraint on language. So there are ways in which language is a constrained system. On the other hand, there are many arguments that say there's an infinite number of possible sentences, and you can establish that by just, stacking them up. So I think there's water on the table. You think that I think that there's water on the table. Your mother thinks that you think that I think the water is on the table. Your brother thinks that maybe your mom is wrong to think that you think that I think, right? So we can make it in sentences of infinite length, or we can stack up adjectives. This is a very silly example, a very, very silly example, a very, 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 very silly example, and so forth. So there are good arguments that there's an infinite range of sentences. In any case, it's vast by any reasonable measure. And for example, almost anything in the physical world we can talk about in the language world. And interestingly, many of the sentences that we understand, we can only understand if we have a very rich model of the physical world. So I don't ultimately want to adjudicate the debate that I think you just set up, but I find it interesting. Maybe the physical world is even more complicated than language. I think that's fair, but
you think that language
is really, really complicated.
It's hard.
It's really, really hard. Well, it's really, really hard for machines, for linguists, people trying to understand it. It's not that hard for children, and that's part of what's driven my whole career. Right? I was a student of Steven Pinker's, and we were trying to figure out why kids could learn language when machines couldn't.
I think we're going to get into language. We're going to get into communication intelligence and neural networks and so on. But let me return to the high level, the futuristic, for a brief moment. So you've written in your new book, it would be arrogant to suppose that we could forecast where AI will be, or the impact it will have in 1,000 years or even 500 years. So let me ask you to be arrogant. What do AI systems with or without physical bodies look like 100 years from now? If you would just, you can't predict, but if you were to philosophize and imagine,
Can I first justify the arrogance before you try to push me beyond it?
Sure.
I mean, there are examples like, people figured out how electricity worked. They had no idea that was going to lead to cell phones, right? I mean, things can move awfully fast once new technologies are perfected. I mean, even when they made transistors, they weren't really thinking that cell phones would lead to social networking.
There are nevertheless predictions of the future, which are statistically unlikely to come to be, but nevertheless is the best.
You're asking me to be wrong.
Asking you to be
Which way would I like to be wrong?
Pick the least unlikely to be wrong thing, even though it's most very likely to be wrong.
I mean, here's some things that we can safely predict, I suppose.
Sure.
We can predict that AI will be faster than it is now. It will be cheaper than it is now. It will be better in the sense of being more general and applicable in more places. It will be pervasive. I mean, these are easy predictions. I'm sort of modeling them in my head on Jeff Bezos' famous predictions. He says, I can't predict the future, not in every way. I'm paraphrasing. But I can predict that people will never want to pay more money for their stuff. They're never going to want it to take longer to get there. And, so like, you can't predict everything, but you can predict some things. Sure, of course, it's going to be faster and better. And what we can't really predict is the full scope of where AI will be in a certain period. I mean, I think it's safe to say that although I'm very skeptical about current AI, that it's possible to do much better. There's no in principle argument that says AI is an insolvable problem, that there's magic inside our brains that will never be captured. I mean, I've heard people make those kind of arguments. I don't think they're very good. So AI is going to come, and probably 500 years is plenty to get there. And then once it's here, it really will change everything.
So when you say AI is going to come, are you talking about human level intelligence? So maybe
I like the term general intelligence. So I don't think that the ultimate AI, if there is such a thing, is going to look just like humans. I think it's going to do some things that humans do better than current machines, like reason flexibly and understand language and so forth. But it doesn't mean they have to be identical to humans. So, for example, humans have terrible memory, and they suffer from what some people call motivated reasoning. So they like arguments that seem to support them, and they dismiss arguments that they don't like. There's no reason that a machine should ever do that.
So you see that the limitations of memory as a bug, not a feature.
Absolutely. I'll say two things about that. One is I was on a panel with Danny Kahneman, the Nobel Prize winner, last night, and we were talking about this stuff. And I think what we converged on is that humans are a low bar to exceed. They may be outside of our skill right now, but as AI programmers, but eventually AI will exceed it. So we're not talking about human level AI. We're talking about general intelligence that can do all kinds of different things and do it without some of the flaws that human beings have. The other thing I'll say is I wrote a whole book actually about the flaws of humans. It's actually a nice bookend to or counterpoint to the current book. So I wrote a book called Klooge, which was about the limits of the human mind. The current book is kind of about those few things that humans do a lot better than machines.
Do you think it's possible that the flaws of the human mind, the limits of memory, our mortality, our bias is a strength, not a weakness, that is the thing that enables from which motivation springs and meaning springs?
I've heard a lot of arguments like this. I've never found them that convincing. I think that there's a lot of making lemonade out of lemons. So yeah. We, for example, do a lot of free association where one idea just leads to the next and they're not really that well connected. And we enjoy that. And we make poetry out of it. And we make kind of movies with free associations, and it's fun and whatever. I don't think that's really a virtue of the system. I think that the limitations in human reasoning actually get us in a lot of trouble. Like, for example, politically, we can't see eye to eye because we have the motivational reasoning I was talking about and something related called confirmation bias. So we have all of these problems that actually make for a rougher society because we can't get along because we can't interpret the data in shared ways. And then we do some nice stuff with that. So my free associations are different from yours, and you're kind of amused by them, and that's great. And hence poetry. So there are lots of ways in which we take a lousy situation and make it good. Another example would be our memories are terrible. So we play games like concentration where you flip over two cards, try to find a pair. Yeah. Can you imagine a computer playing that? Computer's like, this is the dullest game in the world. I know where all the cards are. I see it once. I know where it is. What are you even talking about? So we make a fun game out of having this terrible memory.
So we are imperfect in discovering and optimizing some kind of utility function. But you think in general there is a utility function. There's an objective function that's better than others.
I didn't say that.
But see, the presumption, when you say...
I think you could design a better memory system. You could argue about utility functions and how you want to think about that. But objectively, it would be really nice to do some of the following things. To get rid of memories that are no longer useful. Right. Like objectively, that would just be good. And we're not that good at it. So when you park in the same lot every day, you confuse where you parked today with where you parked yesterday with where you parked the day before and so forth. So you blur together a series of memories. There's just no way that that's optimal. Yeah. I mean, I've heard all kinds of wacky arguments, people trying to defend that. But in the end of the day, I don't think any of them hold water.
Or it's trauma, memories of traumatic events would be possibly a very nice feature to have to get rid of those.
It'd be great if you could just be like, I'm going to wipe this sector. I'm done with that. Yeah. I didn't have fun last night. I don't want to think about it anymore. Whoop, bye-bye.
Gone.
But we can't.
Do you think it's possible to build a system? So you said human level intelligence is a weird concept, but
Well, I'm saying I prefer general intelligence.
general
I mean, human
intelligence.
level intelligence is a real thing, and you could try to make a machine that matches people or something like that.
Right.
I'm saying that per se shouldn't be the objective, but rather that we should learn from humans the things they do well and incorporate that into our AI, just as we incorporate the things that machines do well that people do terribly. So, I mean, it's great that AI systems can do all this brute force computation that people can't. And one of the reasons I work on this stuff is because I would like to see machines solve problems that people can't, that combine the strength, that in order to be solved would combine the strengths of machines to do all this computation with the ability, let's say, of people to read. So, I'd like machines that can read the entire medical literature in a day. 7,000 new papers or whatever the numbers comes out every day. There's no way for, any doctor or whatever to read them all. A machine that could read would be a brilliant thing. And that would be strengths of, brute force computation combined with kind of subtlety and understanding medicine that, a good doctor or scientist has.
So if we can linger a little bit on the idea of general intelligence. So Jan LeCun believes that human intelligence isn't general at all. It's very narrow. How do you think?
I don't think that makes sense. We have lots of narrow intelligences for specific problems. But the fact is, like, anybody can walk into, let's say, a Hollywood movie and reason about the content of almost anything that goes on there. So you can reason about what happens in a bank robbery or what happens when someone is infertile and wants to, go to IVF to try to have a child, or you can, the list is essentially endless. And, not everybody understands every scene in a movie, but there's a huge range of things that pretty much any ordinary adult can understand.
His argument is that actually the set of things seems large to us humans because we're very limited in considering the kind of possibilities of experiences that are possible. But in fact, the amount of experience that are possible is infinitely larger.
Well, I mean, if you want to make an argument that humans are constrained in what they can understand, I have no issue with that. I think that's right. But it's still not the same thing at all as saying, here's a system that can play Go. Right. It's been trained on 5 million games. And then I say, can it play on a rectangular board rather than a square board? And you say, well, if I retrain it from scratch on another 5 million games, it can. That's really, really narrow, and that's where we are. We don't have even a system that could play Go and then without further retraining play on a rectangular board, which any good human could do, with very little problem. So that's what I mean by narrow. And so it's just wordplay to
then
say.
It's semantics. Yeah, then it's just words. Then, yeah, you mean general in a sense that you can do all kinds of Go board shapes flexibly.
Well, I mean, that would be like a first step in the right direction. But obviously, That's not what it really means. You're kidding. What I mean by general is that you could transfer the knowledge you learn in one domain to another. So if you learn about bank robberies in movies and there's chase scenes, then you can understand that amazing scene in Breaking Bad when Walter White has a car chase scene with only one person. He's the only one in it. And you can reflect on how that car chase scene is like all the other car chase scenes you've ever seen and totally different, and why that's cool.
And the fact that the number of domains you can do that with is finite doesn't make it less general. So the idea of general is you could just do it on a lot of transfer it across a lot of domains.
Yeah, I mean, I'm not saying humans are infinitely general or that humans are perfect. Right. I just said, exactly. A minute ago, it's a low bar, but it's just
it's a low bar.
But right now, like the bar is here, and we're there, and eventually we'll get way past it.
So speaking of low bars, you've highlighted in your new book as well, but a couple of years ago wrote a paper titled Deep Learning, a Critical Appraisal that lists 10 challenges faced by current deep learning systems. So let me summarize them as data efficiency, transfer learning, hierarchical knowledge, open-ended inference, explainability, integrating prior knowledge, causal reasoning, modeling an unstable world, robustness, adversarial examples, and so on. And then my favorite probably is reliability and engineering of real-world systems. So whatever people can read the paper, they should definitely read the paper, should definitely read your book. But which of these challenges, if solved, in your view, has the biggest impact on the AI community?
It's a very good question. And I'm going to be evasive because I think that they go together a lot. So, some of them might be solved independently of others, but I think a good solution to AI starts by having real, what I would call cognitive models of what's going on. So right now we have an approach that's dominant where you take statistical approximations of things, but you don't really understand them.
Yes.
So you know that, bottles are correlated in your data with bottle caps, but you don't understand that there's a thread on the bottle cap that fits with the thread on the bottle, and that tightens in. If I tighten enough, that there's a seal and the water can come out. Like, there's no machine that understands that. And having a good cognitive model of that kind of everyday phenomena is what we call common sense. And if you had that, then a lot of these other things start to fall into at least a little bit better place. Because right now, you're like learning correlations between pixels when you play a video game or something like that. And it doesn't work very well. It works when the video game is just the way that you studied it, and then you alter the video game in small ways, like you move the paddle and break out a few pixels, and the system falls apart because it doesn't understand. It doesn't have a representation of a paddle, a ball, a wall, a set of bricks, and so forth. And so it's reasoning at the wrong level.
So the idea of common sense, it's full of mystery. You've worked on it, but it's nevertheless full of mystery. Full of promise. What does common sense mean? What does knowledge mean? So the way you've been discussing it now is very intuitive. It makes a lot of sense that is something we should have, and that's something deep learning systems don't have. But the argument could be that we're oversimplifying it because we're oversimplifying the notion of common sense because that's how it feels like we as humans at the cognitive level approach problems.
So a lot of people aren't actually going to read my book. But if they did read the book, one of the things that might come as a surprise to them is that we actually say common sense is really hard and really complicated. So they would probably, my critics know that I like common sense, but that chapter actually starts by us beating up not on deep learning, but kind of on our own home team, as it will. So Ernie and I are first and foremost people that believe in at least some of what good old-fashioned AI tried to do. So we believe in symbols and logic and programming. Things like that are important. And we go through why even those tools that we hold fairly dear aren't really enough. So we talk about why common sense is actually many things. And some of them fit really well with those classical sets of tools. So things like taxonomy. So I know that a bottle is an object, or it's a vessel, let's say, and I know a vessel is an object, and objects are material things in the physical world. So like I can make some inferences. If I know that vessels need to, not have holes in them, then I can infer that in order, to carry their contents, then I can infer that a bottle shouldn't have a hole in order to carry its contents. So you can do hierarchical inference and so forth. And we say that's great, but it's only a tiny piece of what you need for common sense. We give lots of examples that don't fit into that. So another one that we talk about is a cheese grater. You've got holes in a cheese grater. You've got a handle on top. You can build a model in the game engine sense of a model so that you could have a little cartoon character flying around through the holes of the grater. But we don't have a system yet. Taxonomy doesn't help us that much, that really understands why the handle is on top and what you do with the handle, or why all of those circles are sharp, or how you'd hold the cheese with respect to the grater in order to make it actually work.
Do you think these ideas are just abstractions that could emerge on a system like a very large deep neural network?
I'm a skeptic that kind of emergence per se can work. So I think that deep learning might play a role in the systems that do what I want systems to do, but it won't do it by itself. I've never seen a deep learning system really extract an abstract concept. What they do, principled reasons for that, stemming from how backpropagation works, how the architectures are set up. One example is deep learning people actually all build in something called convolution, which Jan LeCun is famous for, which is an abstraction. They don't have their systems learn this. So the abstraction is that an object looks the same if it appears in different places. And what LeCun figured out, and why, essentially why he was a co-winner of the Turing Award, was that if you program this in innately, then your system would be a whole lot more efficient. In principle, this should be learnable, but people don't have systems that kind of reify things, that make them more abstract. And so what you'd really wind up with if you don't program that in advance is a system that kind of realizes that this is the same thing as this, but then I take your little clock there and I move it over, and it doesn't realize that the same thing applies to the clock.
So the really nice thing, you're right, that convolution is just one of the things that's like it's an innate feature that's programmed by the human expert. But
we need more of those, not
yes.
less.
So yes. But the nice feature is it feels like that requires coming up with that brilliant idea can get you a Turing Award, but it requires less effort than encoding, and something we'll talk about, the expert system. So encoding a lot of knowledge by hand. So it feels like there's a huge amount of limitations, which you clearly outline with deep learning. But the nice feature of deep learning, whatever it is able to accomplish, it does a lot of stuff automatically without human intervention.
Well, and that's part of why people love it, right? But I always think of this quote from Bertrand Russell, which is, it has all the advantages of theft over honest toil. It's really hard to program into a machine a notion of causality, or even how a bottle works or what containers are. Ernie Davis and I wrote a 45-page academic paper trying just to understand what a container is, which I don't think anybody ever read the paper, but it's a very detailed analysis of all the things. Well, not even all of it. Some of the things you need to do in order to understand a container. It would be a whole lot nice. And, I'm a co-author on the paper. I made it a little bit better, but Ernie did the hard work for that particular paper. And it took him like 3 months to get the logical statements correct. And maybe that's not the right way to do it. It's a way to do it. But on that way of doing it, it's really hard work to do something as simple as understanding containers. And nobody wants to do that hard work. Even Ernie didn't want to do that hard work. Everybody would rather just like feed their system in with a bunch of videos with a bunch of containers and have the systems infer how containers work. It would be like so much less effort. Let the machine do the work. And so I understand the impulse. I understand why people want to do that. I just don't think that it works. I've never seen anybody build a system that in a robust way can actually watch videos and predict exactly, which containers would leak and which ones wouldn't, or something like. And I know someone's going to go out and do that since I said it, and I look forward to seeing it. But getting these things to work robustly is really, really hard. So Jan LeCun, who was my colleague at NYU for many years, thinks that the hard work should go into defining an unsupervised learning algorithm that will watch videos, use the next frame basically in order to tell it what's going on. And he thinks that's the royal road, and he's willing to put in the work in devising that algorithm. Then he wants the machine to do the rest. And again, I understand the impulse. My intuition, based on years of watching this stuff and making predictions 20 years ago that still hold, even though there's a lot more computation and so forth, is that we actually have to do a different kind of hard work, which is more like building a design specification for what we want the system to do, doing hard engineering work to figure out how we do things like what Jan did for convolution in order to figure out how to encode complex knowledge into the systems. The current systems don't have that much knowledge other than convolution, which is, again, this, objects being in different places and having the same perception, I guess I'll say, same appearance. People don't want to do that work. They don't see how to naturally fit one with the other.
I think that's, yes, absolutely. But also on the expert system side, there's a temptation to go too far the other way. So which is having an expert sort of sit down and encode the description, the framework for what a container is, and then having the system reason the rest. From my view, like one really exciting possibility is of active learning, where it's continuous interaction between a human and machine. As the machine, there's kind of deep learning type extraction of information from data, patterns, and so on, but humans also guiding the learning procedures, guiding the both the process and the framework of how the machine learns, whatever the task is.
I was with you with almost everything you said except the phrase deep learning. What I think you really want there is a new form of machine learning. So let's remember, deep learning is a particular way of doing machine learning. Most often it's done with supervised data for perceptual categories. There are other things you can do with deep learning, some of them quite technical, but the standard use of deep learning is I have a lot of examples and I have labels for them. So here are pictures. This one's the Eiffel Tower. This one's the Sears Tower. This one's the Empire State Building. This one's a cat. This one's a pig, and so forth. You just get, millions of examples, millions of labels. And deep learning is extremely good at that. It's better than any other solution that anybody has devised. But it is not good at representing abstract knowledge. It's not good at representing things like bottles contain liquid and have tops to them and so forth. It's not very good at learning or representing that kind of knowledge. It is an example of having a machine learn something,
Right.
but it's a machine that learns a particular kind of thing, which is object classification. It's not a particularly good algorithm for learning about the abstractions that govern our world. There may be such a thing. Part of what we counsel in the book is maybe people should be working on devising such things.
So one possibility, just I wonder what you think about it, is so deep neural networks do form abstractions, but they're not accessible to us humans in terms of we can't.
There's some truth in that.
So is it possible that either current or future neural networks form very high-level abstractions which are as powerful as our human abstractions of common sense? We just can't get a hold of them. And so the problem is essentially what we need to make them explainable.
This is an astute question, but I think the answer is at least partly no. One of the kinds of classical neural network architectures is what we call an auto-associator. It just tries to take an input, goes through a set of hidden layers, and comes out with an output. And it's supposed to learn essentially the identity function, that your input is the same as your output. So you think of it as binary numbers. You've got like the 1, the 2, the 4, the 8, the 16, and so forth. And so if you want to input 24, you turn on the 16, you turn on the 8. It's like binary 1, 1, and a bunch of zeros. So I did some experiments in 1998 with the precursors of contemporary deep learning. And what I showed was you could train these networks on all the even numbers, and they would never generalize to the odd number. A lot of people thought that I was, I don't know, an idiot or faking the experiment or wasn't true or whatever. But it is true that with this class of networks that we had in that day, that they would never, ever make this generalization. And it's not that the networks were stupid. It's that they see the world in a different way than we do. They were basically concerned, what is the probability that the rightmost output node is going to be a 1? And as far as they were concerned, in everything they'd ever been trained on, it was a 0. That node had never been turned on. And so they figured, why turn it on now? Whereas a person would look at the same problem and say, well, it's obvious. We're just doing the thing that corresponds. The Latin for it is mutatis mutandis. We'll change what needs to be changed. And we do this. This is what algebra is. So right. I can do f of x equals y plus 2. And I can do it for a couple of values. I can tell you if y is 3, then x is 5. And if y is 4, x is 6. And now I can do it with some totally different number, like 1,000,000. Then you can say, well, obviously it's 1,000,002 because you have an algebraic operation that you're applying to a variable. And deep learning systems kind of emulate that, but they don't actually do it. The particular example, you could fudge a solution to that particular problem. The general form of that problem remains that what they learn is really correlations between different input and output nodes. And they're complex correlations with multiple nodes involved and so forth, but they're correlative. They're not structured over these operations over variables. Now, someday people may do a new form of deep learning that incorporates that stuff, and I think it will help a lot. And there's some tentative work on things like differentiable programming right now that fall into that category. But the sort of classic stuff like people use for ImageNet doesn't have it. And you have people like Hinton going around saying symbol manipulation, like what I advocate, is like the gasoline engine. It's obsolete. We should just use this cool electric power that we've got with the deep learning. And that's really destructive because we really do need to have the gasoline engine stuff that represents, I don't think it's a good analogy, but we really do need to have the stuff that represents symbols.
Yeah. And Hinton as well would say that we do need to throw out everything and start over. So, there's a notion.
Hinton said that to Axios. And I had a friend who interviewed him and tried to pin him down on what exactly we need to throw out. And he was very evasive.
Well, of course, because we can't. If he knew,
then he'd throw it out himself. But you can't have it both ways. You can't be like, I don't know what to throw out, but I am going to throw out the symbols. And not just the symbols, but the variables and the operations over variables. And don't forget, the operations over variables, the stuff that I'm endorsing and which, John McCarthy did when he founded AI, that stuff is the stuff that we build most computers out of. There are people now who say, we don't need computer programmers anymore. Not quite looking at the statistics of how much computer programmers actually get paid right now. We need lots of computer programmers. And most of them, they do a little bit of machine learning, but they still do a lot of code, right? Code where it's like, if the value of X is greater than the value of Y, then do this kind of thing, like conditionals and comparing operations over variables. Like there's this fantasy you can machine learn anything. There's some things you would never want to machine learn. I would not use a phone operating system that was machine learned. Like you made a bunch of phone calls and you recorded which packets were transmitted and you just machine learned it. It'd be insane. Or to build a web browser by taking logs of keystrokes and images, screenshots, and then trying to learn the relation between them. No rational person would ever try to build a browser that they would use symbol manipulation, the stuff that I think AI needs to avail itself of in addition to deep learning.
Can you describe what your view of symbol manipulation in its early days? Can you describe expert systems and where do you think they hit a wall or a set of challenges?
Sure. So, first, I just want to clarify. I'm not endorsing expert systems per se. You've been kind of contrasting them. There is a contrast, but that's not the thing that I'm endorsing.
Yes.
So expert systems try to capture things like medical knowledge with a large set of rules. So if the patient has this symptom and this other symptom, then it is likely that they have this disease. So there are logical rules, and they were symbol manipulating rules of just the sort that I'm talking about. And they
encode a set of knowledge that the experts then put in.
And very explicitly so. So you'd have somebody interview an expert and then try to turn that stuff into rules. Yeah. And at some level, I'm arguing for rules. But the difference is those guys did in the 80s was almost entirely rules, almost entirely handwritten with no machine learning. What a lot of people are doing now is almost entirely one species of machine learning with no rules. And what I'm counseling is actually a hybrid. I'm saying that both of these things have their advantage. So if you're talking about perceptual classification, how do I recognize a bottle? Deep learning is the best tool we've got right now. If you're talking about making inferences about what a bottle does, something closer to the expert systems is probably still the best available alternative. And probably we want something that is better able to handle quantitative and statistical information than those classical systems typically were. So we need new technologies that are going to draw some of the strengths of both the expert systems and the deep learning, but are going to find new ways to synthesize them.
How hard do you think it is to add knowledge at the low level? So mine human intellects to add extra information to symbol manipulating systems?
In some domains, it's not that hard, but it's often really hard. Partly because a lot of the things that are important, people wouldn't bother to tell you. So if you pay someone on Amazon Mechanical Turk to tell you stuff about bottles, they probably won't even bother to tell you some of the basic level stuff that's just so obvious to a human being and yet so hard to capture in machines. They're going to tell you more exotic things, and like they're all well and good, but they're not getting to the root of the problem. So untutored humans aren't very good at knowing, and why should they be, what kind of knowledge the computer system developers actually need. I don't think that that's an irremediable problem. I think it's historically been a problem. People have had crowdsourcing efforts, and they don't work that well. There's one at MIT, we're recording this at MIT, called Virtual Home, where, and we talk about this in the book, find the exact example there, but people were asked to do things like describe an exercise routine. And the things that the people describe are very low level and don't really capture what's going on. So they're like, go to the room with the television and the weights, turn on the television, press the remote to turn on the television, lift weight, put weight down, or whatever. It's like very micro level. And it's not telling you what an exercise routine is really about, which is like, I want to fit a certain number of exercises in a certain time period. I want to emphasize these muscles. I mean, you want some kind of abstract description. The fact that you happen to press the remote control in this room when you watch this television isn't really the essence of the exercise routine. But if you just ask people, like, what did they do? Then they give you this fine grain. And so it takes a level of expertise about how the AI works in order to craft the right kind of knowledge.
So there's this ocean of knowledge that we all operate on. Some of it may not even be conscious, or at least we're not able to communicate it effectively.
Yeah, most of it we would recognize if somebody said it, if it was true or not, right. But we wouldn't think to say that it's true or not.
It's a really interesting mathematical property this ocean has the property that every piece of knowledge in it, we will recognize it as true if we're told, but we're unlikely to retrieve it in the reverse. So
Exactly.
that interesting property, I would say there's a huge ocean of that knowledge. What's your intuition? Is it accessible to AI systems somehow? Can we? So you
Not
said
yet. I mean, most of it is not. Well, I'll give you an asterisk on this in a second, but most of it is not ever been encoded in machine interpretable form. And so, I mean, if you say accessible, there's two meanings of that. One is like, could you build it into a machine? Yes. The other is like, is there some database that we could go, download and stick into our
the
machine?
first thing,
no.
Could we? What's your intuition?
I think we could. I think it hasn't been done right. The closest, and this is the asterisk, is the CYC psych system. Tried to do this. A lot of logicians worked for Doug Lenat for 30 years on this project. I think they stuck too closely to logic, didn't represent enough about probabilities, tried to hand code it. There are various issues, and it hasn't been that successful. That is the closest existing system to trying to encode this.
Why do you think there's not more excitement / money behind this idea currently?
There was. People view that project as a failure. I think that they confuse the failure of a specific instance that was conceived 30 years ago for the failure of an approach, which they don't do for deep learning. Yeah. So, in 2010, people had the same attitude towards deep learning. They're like, this stuff doesn't really work. And, all these other algorithms work better and so forth. And then certain key technical advances were made, but mostly it was the advent of graphics processing units that changed that. It wasn't even anything foundational in the techniques. And there was some new tricks, but mostly it was just more compute and more data, things like ImageNet that didn't exist before, that allowed deep learning. And it could be, to work, it could be that, Psych just needs a few more things or something like Psych. But the widespread view is that just doesn't work. And people are reasoning from a single example. They don't do that with deep learning. They don't say nothing that existed in 2010, and there were many, many efforts in deep learning was really worth anything, right? I mean, really, there's no model from 2010 in deep learning or the predecessors to deep learning that has any commercial value whatsoever at this point, right? They're all failures. But that doesn't mean that there wasn't anything there. I have a friend, I was getting to know him, and he said, I had a company too. I was talking about I had a new company. He said, I had a company too, and it failed. And I said, well, what did you do? And he said, deep learning. And the problem was he did it in 1986 or something like that. And we didn't have the tools then, or 1990. We didn't have the tools then, not the algorithms. His algorithms weren't that different from modern algorithms, but he didn't have the GPUs to run it fast enough. He didn't have the data. And so it failed. It could be that, symbol manipulation per se, with modern amounts of data and compute and maybe some advance in compute for that kind of compute, might be great. My perspective on it is not that we want to resuscitate that stuff per se, but we want to borrow lessons from it, bring together with other things that we've learned.
And it might have an ImageNet moment where it will spark the world's imagination, and there'll be an explosion of symbol manipulation efforts.
Yeah, I think that people at AI2, Paul Allen's AI Institute, are trying to do that. They're trying to build data sets that, well, they're not doing it for quite the reason that you say, but they're trying to build data sets that at least spark interest in common sense reasoning.
So create benchmarks.
Benchmarks for common sense. That's a large part of what the AI2.org is working on right now.
So speaking of compute, Rich Sutton wrote a blog post titled Bitter Lesson. I don't know if you've read it, but he said that the biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective. Do you think
most effective at what? Right. So they have been most effective for perceptual classification problems and for some reinforcement learning problems. He works on reinforcement learning.
Well, no, let me push back on that. You're actually absolutely right. But I would also say they have been most effective generally because everything we've done up to... would you argue against that? To me, deep learning is the first thing that has been successful at anything in AI. And you're pointing out that this success is very limited, folks. But has there been something truly successful before deep learning?
Sure. I mean, I want to make a larger point, but
Sure.
on the narrower point, classical AI is used, for example, in doing navigation instructions.
Sure. All
It's
kind of
very
search,
successful.
also,
Everybody on the planet uses it now, like multiple times a day.
Yeah.
That's a measure of success, right? So, I mean, I don't think classical AI was wildly successful, but there are cases like that. They're just used all the time. Nobody even notices them because they're so pervasive. So there are some successes for classical AI. I think deep learning has been more successful. But my usual line about this, and I didn't invent it, but I like it a lot, is just because you can build a better ladder doesn't mean you can build a ladder to the moon. So the bitter lesson is if you have a perceptual classification problem, throwing a lot of data at it is better than anything else. But that has not given us any material progress in natural language understanding, common sense reasoning like a robot would need to navigate a home. Problems like that, there's no actual progress there.
So, flip side of that, if we remove data from the picture, another bitter lesson is that you just have a very simple algorithm and you wait for compute to scale. It doesn't have to be learning. It doesn't have to be deep learning. It doesn't have to be data driven, but just wait for the compute. So my question for you, do you think compute can unlock some of the things with either deep learning or symbol manipulation that?
Sure, but I'll put a proviso on that. Like more compute's always better. Like nobody's going to argue with more compute. It's like having more money. I mean,
there's diminishing
data
returns are more money. Right?
Exactly. There's diminishing returns on more money, but nobody's going to argue if you want to give them more money, right? Except maybe the people who signed the giving pledge, and some of them have a problem. They've promised to give away more money than they're able to. But the rest of us, if you want to give me more money, fine.
Say more money, more problems, but okay. Yeah,
that's true too. What I would say to you is your brain uses like 20 watts. And it does a lot of things that deep learning doesn't do, or the symbol manipulation doesn't do, that AI just hasn't figured out how to do. So it's an existence proof that you don't need, server resources that are Google scale in order to have an intelligence. I built, with a lot of help from my wife, 2 intelligences that are 20 watts each and far exceed anything that anybody else has built out of silicon.
Speaking of those 2 robots, what have you learned about AI from having?
Well, they're not robots, but
intelligent agents.
There's 2 intelligent agents. I've learned a lot by watching my 2 intelligent agents. I think that what's fundamentally interesting, well, one of the many things that's fundamentally interesting about them is the way that they set their own problems to solve. So my 2 kids are a year and a half apart. They're both 5 and 6.5. They play together all the time, and they're constantly creating new challenges. Like that's what they do, is they make up games. And they're like, well, what if this, or what if that, or what if I had this superpower, or what if you could walk through this wall. So they're doing these what if scenarios all the time, and that's how they learn something about the world and grow their minds. And machines don't really do that.
So that's interesting. And you've talked about this, you've written about it, you've thought about it, nature versus nurture. So what innate knowledge do you think we're born with? And what do we learn along the way in those early months and years?
Can I just say how much I like that question? You phrased it just right, and almost nobody ever does. Which is, what is the innate knowledge and what's learned along the way? So many people dichotomize it and they think it's nature versus nurture, when it is obviously has to be nature and nurture. They have to work together. You can't learn the stuff along the way unless you have some innate stuff. But just because you have the innate stuff doesn't mean you don't learn anything. And so many people get that wrong, including in the field. Like people think, if I work in machine learning, the learning side, I must not be allowed to work on the innate side, or that
cheating.
will be cheating. Yeah. Exactly. People have said that to me. And it's just absurd. Yeah. So thank you.
But, you could break that apart more. I've talked to folks who study the development of the brain. And I mean, the growth of the brain in the first few days, in the first few months, in the womb, all of that, is that innate? So that process of development, from a stem cell to the growth of the central nervous system and so on, to the information that's encoded through the long arc of evolution. So all of that comes into play, and it's unclear. It's not just whether it's a dichotomy or not. It's where most or where the knowledge is encoded. So what's your intuition about the innate knowledge, the power of it, what's contained in it? What can we learn from it?
One of my earlier books was actually trying to understand the biology of this. The book was called The Birth of the Mind. Like, how is it the genes even build innate knowledge?
Yes.
And from the perspective of the conversation we're having today, there's actually two questions. One is what innate knowledge or mechanisms or what have you people or other animals might be endowed with. I always like showing this video of a baby ibex climbing down a mountain. That baby ibex, a few hours after its birth, knows how to climb down a mountain. That means that it knows, not consciously, something about its own body and physics and 3D geometry and all of this kind of stuff. So there's one question about, like, what does biology give its creatures? What is evolved in our brains? How is that represented in our brains? The question I thought about in the book, The Birth of the Mind. And then there's a question of what AI should have. And they don't have to be the same. But I would say that, it's a pretty interesting set of things that we are equipped with that allows us to do a lot of interesting things. So I would argue or guess, based on my reading of the developmental psychology literature, which I've also participated in, that children are born with a notion of space, time, other agents, places, and also this kind of mental algebra that I was describing before. Notion of causation, if I didn't just say that. So at least those kinds of things. They're like frameworks for learning the other things. So
are they disjoint in your view, or is it just somehow all connected? You've talked a lot about language. Is it all kind of connected in some mesh that's language-like, of understanding concepts altogether? Or
I don't think we know for people how they're represented, and machines just don't really do this yet. So I think it's an interesting open question, both for science and for engineering. Some of it has to be at least interrelated in the way that, like, the interfaces of a software package have to be able to talk to one another. So, right. The systems that represent space and time can't be totally disjoint, because a lot of the things that we reason about are relations between space and time and cause. So, I put this on and I have expectations about what's going to happen with the bottle cap on top of the bottle. And those span space and time. If the cap is over here, I get a different outcome. If the timing is different, if I put this here after I move that, then, I get a different outcome. That relates to causality. So obviously these mechanisms, whatever they are, can certainly communicate with each other.
So I think evolution had a significant role to play in the development of this whole kludge, right? How efficient do you think is evolution?
Oh, it's terribly inefficient, except that...
Okay, well, can we do better?
Well, I'll come to that in a second.
Sure.
It's inefficient, except that once it gets a good idea, it runs with it. So it took, I guess, 1 billion years, roughly 1 billion years, to evolve to a vertebrate brain plan. And once that vertebrate plan evolved, it spread everywhere. So fish have it, and dogs have it, and we have it. We have adaptations of it and specializations of it. But and the same thing with a primate brain plan. So monkeys have it, and apes have it, and we have it. So, there are additional innovations like color vision, and those spread really rapidly. So it takes evolution a long time to get a good idea, but and I'm, being anthropomorphic and not literal here. Right. But once it has that idea, so to speak, which cashes out into once a set of genes are in the genome, those genes spread very rapidly. And they're like subroutines or libraries, I guess is the word people might use nowadays or be more familiar with. They're libraries that can get used over and over again. Yeah. So once you have the library for building something with multiple digits, you can use it for a hand, but you can also use it for a foot. And you just kind of reuse the library with slightly different parameters. Evolution does a lot of that, which means that the speed over time picks up. So evolution can happen faster because you have bigger and bigger libraries. And what I think has happened in attempts at evolutionary computation is that people start with libraries that are very, very minimal, like almost nothing. And then progress is slow and it's hard for someone to get a good PhD thesis out of it and they give up. If we had richer libraries to begin with, if you were evolving from systems that had a rich innate structure to begin with, then things might speed up.
Or more PhD students, if the evolutionary process is indeed in a meta way, runs away with good ideas, you need to have a lot of ideas, pool of ideas, in order for it to discover one that you can run away with. And PhD students representing individual ideas as well.
Yeah, I mean, you could throw a billion PhD students at it.
Yeah. The monkeys at typewriters with Shakespeare. Yep.
Well, but, I mean, those aren't cumulative, right? That's just random. And part of the point that I'm making is that evolution is cumulative. So if
Exactly.
you have a billion monkeys independently,
Yeah.
you don't really get anywhere. But if you have a billion monkeys, and I think Dawkins made this point originally, or probably other people, Dawkins made it very nice in either Selfish Gene or Blind Watchmaker. If there's some sort of fitness function that can drive you towards something, I guess that's Dawkins' point. And my point, which is a variation on that, is that if the evolution is cumulative, the related points, then you can start going faster.
Do you think something like the process of evolution is required to build intelligent systems? So if we
Not logically. So all the stuff that evolution did, a good engineer might be able to do. So for example, evolution made quadrupeds, which distribute the load across a horizontal surface. A good engineer could come up with that idea. Sometimes good engineers come up with ideas by looking at biology. There's lots of ways to get your ideas. Part of what I'm suggesting is we should look at biology a lot more. We should look at the biology of thought and understanding, and the biology by which creatures intuitively reason about physics or other agents, or like how do dogs reason about people? Like they're actually pretty good at it. If we could understand, at my college we joked dognition. If we could understand dognition well and how it was implemented, that might help us with our AI.
So do you think it's possible that the kind of timescale that evolution took is the kind of timescale that will be needed to build intelligent systems? Or can we significantly accelerate that process inside a computer?
I think the way that we accelerate that process is we borrow from biology. Not slavishly, but I think we look at how biology has solved problems and we say, does that inspire any engineering solutions here?
Try to mimic biological systems and then therefore have a shortcut.
Yeah, there's a field called biomimicry, and people do that for like material science all the time. We should be doing the analog of that for AI. And the analog for that for AI is to look at cognitive science or the cognitive sciences, which is psychology, maybe neuroscience, linguistics, and so forth. Look to those for insight.
What do you think is a good test of intelligence in your view? So
I don't think there's one good test. In fact, I tried to organize a movement towards something called a Turing Olympics, and my hope is that Francois Chalet is going to take over this. I think he's interested in. I just don't have a place in it in my busy life at this moment. But the notion is that there'll be many tests and not just one, because intelligence is multifaceted. There can't really be a single measure of it because it isn't a single thing. Like just at the crudest level, the SAT has a verbal component and a math component because they're not identical. And Howard Gardner has talked about multiple intelligence, like kinesthetic intelligence and verbal intelligence and so forth. There are a lot of things that go into intelligence, and people can get good at one or the other. In some sense, like every expert has developed a very specific kind of intelligence, and then there are people that are generalists, and like I think of myself as a generalist with respect to cognitive science, which doesn't mean I know anything about quantum mechanics, but I know a lot about the different facets of the mind. And, there's a kind of intelligence to thinking about intelligence. I like to think that I have some of that, but social intelligence, I'm just okay. There are people that are much better at that than I am.
Sure. But what would be really impressive to you? I think the idea of a Turing Olympics is really interesting, especially if somebody like Francois is running it. But to you in general, not as a benchmark, but if you saw an AI system being able to accomplish something that would impress the heck out of you, what would that thing be? Would it be natural language conversation?
For me personally, I would like to see a kind of comprehension that relates to what you just said. So I wrote a piece in the New Yorker in, I think, 2015, right after Eugene Gustman, which is a software package, won a version of the Turing test. And the way that it did this is the way you win the Turing test, so called win it, is, the Turing test is you fool a person into thinking that a machine is a person, is you're evasive, you pretend to have limitations so you don't have to answer certain questions, and so forth. So this particular system pretended to be a 13-year-old boy from Odessa who didn't understand English and was kind of sarcastic and wouldn't answer your questions and so forth. And so judges got fooled into thinking, briefly with a very little exposure, it was a 13-year-old boy. And it ducked all the questions that Turing was actually interested in, which is like, how do you make the machine actually intelligent? Mm-hmm. So that test itself is not that good. And so in New Yorker, I proposed an alternative, I guess. And the one that I proposed there was a comprehension test. And I must like Breaking Bad because I've already given you one Breaking Bad example. And in that article, I have one as well, which was like something like, if Walter White, you should be able to watch an episode of Breaking Bad, or maybe you have to watch the whole series to be able to answer the question and say, if Walter White took a hit out on Jesse, why did he do that? Right. So if you could answer kind of arbitrary questions about characters' motivations, I would be really impressed with that. I mean, you build software to do that. They could watch a film, or there are different versions. And so ultimately, I wrote this up with Praveen Paratosh in a special issue of AI magazine that basically was about the Turing Olympics. There were like 14 tests proposed. And the one that I was pushing was a comprehension challenge. And Praveen, who's at Google, was trying to figure out like how we would actually run it. And so we wrote a paper together. And you could have a text version too, or you could have an auditory podcast version, you could have a written version. But the point is that you win at this test if you can do, let's say, human level or better than humans at answering kind of arbitrary questions. Why did this person pick up the stone? What were they thinking when they picked up the stone? Were they trying to knock down glass? And I mean, ideally, these wouldn't be multiple choice either, because multiple choice is pretty easily gamed. So if you could have relatively open-ended questions and you can answer why people are doing this stuff, I would be very impressed. And of course, humans can do this, right? If you watch a well-constructed movie and somebody picks up a rock, everybody watching the movie knows why they picked up the rock, right? They all know, oh my gosh, he's going to, hit this character or whatever. We have an example in the book about when a whole bunch of people say, I am Spartacus, this famous scene. The viewers understand, first of all, that everybody or everybody minus one has to be lying. They can't all be Spartacus. We have enough common sense knowledge to know they couldn't all have the same name. We know that they're lying, and we can infer why they're lying, right? They're lying to protect someone and to protect things they believe in. You get a machine that can do that. They can say, this is why these guys all got up and said, I am Spartacus. I will sit down and say, AI has really achieved a lot. Thank you.
Without cheating any part of the system.
Yeah, I mean, if you do it, there are lots of ways you could cheat. Like you could build a Spartacus machine that works on that film. Like that's not what I'm talking about. I'm talking about you can do this with essentially arbitrary films, or from a large
even
set.
Beyond films, because it's possible such a system would discover that the number of narrative arcs in film is like limited to like
there's
90,
a famous
30.
thing about the classic 7 plots or whatever.
Right.
I don't care if you want to build in the system, boy meets girl, boy loses girl, boy finds girl. That's fine. I don't mind having some head start.
Innate knowledge. Okay. Good.
I mean, you could build it in innately, or you could have your system watch a lot of films again. If you can do this at all, but with a wide range of films, not just one film in one genre. But even if you could do it for all Westerns, I'd be reasonably impressed.
Yeah. So in terms of being impressed, just for the fun of it, because you've put so many interesting ideas out there in your book, challenging the community for further steps, is it possible on the deep learning front that you're wrong about its limitations, that deep learning will unlock? Jan LeCun next year will publish a paper that achieves this comprehension. So do you think that way often as a scientist? Do you consider that your intuition, that deep learning could actually run away with it?
I'm more worried about rebranding as a kind of political thing. So I mean, what's going to happen, I think, is that deep learning is going to start to encompass symbol manipulation. So I think Hinton's just wrong. Hinton says we don't want hybrids. I think people will work towards hybrids and they will relabel their hybrids as deep learning. We've already seen some of that. So AlphaGo is often described as a deep learning system, but it's more correctly described as a system that has deep learning, but also Monte Carlo tree search, which is a classical AI technique. And people will start to blur the lines in the way that IBM blurred Watson. First, Watson meant this particular system, and then it was just anything that IBM built in their cognitive division.
Sure, but purely, let me ask for sure. That's a branding question, and that's like a giant mess. I mean, purely a single neural network being able to accomplish.
I don't stay up at night worrying that that's going to happen. And I'll just give you two examples. One is a guy at DeepMind thought he had finally outfoxed me. Yeah. At Zergy Lord, I think is his Twitter handle. Uh-huh. And he said, he specifically made an example. Marcus said that such and such. He fed it into GP2, which is the AI system that is so smart that OpenAI couldn't release it because it would destroy the world, right? Yes. You remember that a few months ago. So he feeds it into GPT-2. And my example was something like a rose is a rose, a tulip is a tulip, a lily is a blank. And he got it to actually do that, which was a little bit impressive. And I wrote back and I said, that's impressive, but can I ask you a few questions? I said, can it, was that just one example? Can it do it generally? And can it do it with novel words, which was part of what I was talking about in 1998 when I first raised the example. So a DAX is a DAX, right? Mm-hmm. And he sheepishly wrote back about 20 minutes later. And the answer was, well, it had some problems with those. So, I made some predictions 21 years ago that still hold. In the world of computer science, that's amazing, right? Because, there's 1,000 or 1,000,000 times more memory and, computations 1,000,000 times, do 1,000,000 times more operations per second, spread across a cluster. And there's been advances in, replacing sigmoids with other functions and so forth. There's all kinds of advances, but the fundamental architecture hasn't changed and the fundamental limit hasn't changed. And what I said then is kind of still true. And then here's a second example. I recently had a piece in Wired that's adapted from the book, and the book went to press before GP2 came out. Mm-hmm. But we describe this children's story and all the inferences that you make in this story about a boy finding a lost wallet. And for fun, in the Wired piece, we ran it through GPT-2 at something called talktotransformer.com, and your viewers can try this experiment themselves. Go to the Wired piece that has the link and it has the story. And the system made perfectly fluent text that was totally inconsistent with the conceptual underpinnings of the story. Mm-hmm. Right. And this is what, again, I predicted in 1998. And for that matter, Chomsky and Miller made the same prediction in 1963. I was just updating their claim for a slightly new text. So those particular architectures that don't have any built-in knowledge, they're basically just a bunch of layers doing correlational stuff. They're not going to solve these problems.
So 20 years ago, you said the emperor has no clothes. Today, the emperor still has no clothes.
The lighting's better, though.
The lighting is better. And I think you yourself are also,
And we found out some things to do with naked emperors. It's not that exactly. Stuff is worthless. They're not really naked. It's more like they're in their briefs and everybody thinks that. And so, they are great at speech recognition. Yes. But the problems that I said were hard, because I didn't literally say the emperor has no clothes. I said, this is a set of problems that humans are really good at. And it wasn't couched as AI. It was couched as cognitive science. But I said, if you want to build a neural model of how humans do certain class of things, you're going to have to change the architecture. And I stand by those claims.
So, and I think people should understand you're quite entertaining in your cynicism, but you're also very optimistic and a dreamer about the future of AI too. So you're both.
There's a famous saying about being people overselling technology in the short run and underselling it in the long run. Right. And so I actually end the book, or Ernie Davis and I end our book with an optimistic chapter, which kind of killed Ernie because he's even more pessimistic than I am. He describes me as a contrarian and him as a pessimist. But I persuaded him that we should end the book with a look at what would happen if AI really did incorporate, for example, the common sense reasoning and the nativism and so forth, the things that we counseled for. And we wrote it, and it's an optimistic chapter that AI suitably reconstructed so that we could trust it, which we can't now, could really be world changing.
So on that point, if you look at the future trajectories of AI, people have worries about negative effects of AI, whether it's at the large existential scale or smaller short-term scale of negative impact on society. So you're right about trustworthy AI. How can we build AI systems that align with our values, that make for a better world, that we can interact with, that we can trust?
The first thing we have to do is to replace deep learning with deep understanding. So you can't have alignment with a system that traffics only in correlations and doesn't understand concepts like bottles or harm. So Asimov talked about these famous laws, and the first one was first do no harm. And you can quibble about the details of Asimov's laws, but we have to, if we're going to build real robots in the real world, have something like that. That means we have to program in a notion that's at least something like harm. That means we have to have these more abstract ideas that deep learning is not particularly good at. They have to be in the mix somewhere. I mean, you could do statistical analysis about probabilities of given harms or whatever, but you have to know what a harm is in the same way that you have to understand that a bottle isn't just a collection of pixels.
And also be able to, you're implying that you need to also be able to communicate that to humans. So the AI systems would be able to prove to humans that they understand, that they know what harm means.
I might run it in the reverse direction, but roughly speaking, I agree with you. So we probably need to have committees of wise people, ethicists and so forth, think about what these rules ought to be. And we shouldn't just leave it to software engineers. It shouldn't just be software engineers. And it shouldn't just be, people who own large mega corporations that are good at technology. Ethicists and so forth should be involved. But, there should be some assembly of wise people, as I was putting it, that tries to figure out what the rules ought to be. And those have to get translated into code. You can argue, or code or neural networks or something. They have to be translated into something that machines can work with. And that means there has to be a way of working the translation. And right now we don't. We don't have a way. So let's say you and I were the committee and we decide that Asimov's first law is actually right. And let's say it's not just two white guys, which would be kind of unfortunate, and that we have a broad, and so we have a representative sample of the world, or however we want to do this. And the committee decides eventually, okay, Asimov's first law is actually pretty good. There are these exceptions to it. We want to program in these exceptions, but let's start with just the first one and then we'll get to the exceptions. First one is first do no harm. Well, somebody has to now actually turn that into a computer program or a neural network or something. And one way of taking the whole book, the whole argument that I'm making, is that we just don't know how to do that yet. And we're fooling ourselves if we think that we can build trustworthy AI if we can't even specify in any kind of, we can't do it in Python and we can't do it in TensorFlow. We're fooling ourselves in thinking that we can make trustworthy AI if we can't translate harm into something that we can execute. And if we can't, then we should be thinking really hard, how could we ever do such a thing? Because if we're going to use AI in the ways that we want to use it, to make job interviews or to do surveillance, not that I personally want to do that or whatever. I mean, if we're going to use AI in ways that have practical impact on people's lives or medicine, it's got to be able to understand stuff like that.
So one of the things your book highlights is that, a lot of people in the deep learning community, but also the general public, politicians, just people in all general groups and walks of life have different levels of misunderstanding of AI. So when you talk about committees, what's your advice to our society? How do we grow? How do we learn about AI such that such committees could emerge, where large groups of people could have a productive discourse about how to build successful AI systems?
Part of the reason we wrote the book was to try to inform those committees. So part of the reason we wrote the book was to inspire a future generation of students to solve what we think are the important problems. So a lot of the book is trying to pinpoint what we think are the hard problems where we think effort would most be rewarded. And part of it is to try to train people who talk about AI but aren't experts in the field to understand what's realistic and what's not. One of my favorite parts in the book is the 6 questions you should ask anytime you read a media account. So like number 1 is if somebody talks about something, look for the demo. If there's no demo, don't believe it. Like the demo that you can try. If you can't try it at home, maybe it doesn't really work that well yet. So if we don't have this example in the book, but if Sundar Pichai says, we have this thing that allows it to sound like human beings in conversation, you should ask, can I try it? And you should ask how general it is. And it turns out at that time, I'm alluding to Google Duplex, when it was announced, it only worked on calling hairdressers, restaurants, and finding opening hours. That's not very general. That's narrow AI.
And I'm not going to ask your thoughts about Sophia, but yeah, I understand that's a really good question to ask of any kind of hyped up idea.
Sophia has very good material written for her, but she doesn't understand the things that she's saying.
So a while ago, you've written a book on the science of learning, which I think is fascinating, but the learning case studies of playing guitar.
That's right.
Called Guitar Zero. I love guitar myself. I've been playing my whole life. So let me ask a very important question. What is your favorite song, rock song, to listen to or try to play?
Well, those would be different. But I'll say that my favorite rock song to listen to is probably All Along the Watchtower, the Jimi Hendrix version.
The Jimi Hendrix version.
It just feels magic to me.
I've actually recently learned it. I love that song. I've been trying to put it on YouTube myself singing. Singing is the scary part. If you could party with a rock star for a weekend, living or dead, who would you choose? And pick their mind. It's not necessarily about the partying.
Thanks for the clarification. I guess John Lennon's such an intriguing person, and I think a troubled person, but an intriguing one. So
beautiful. Well, Imagine is one of my favorite songs. So
also one of my favorite songs.
That's a beautiful way to end it. Gary, thank you so much for talking today.
Thanks so much for having me.